2.4, we're going to be solving equations that are known as exact equations. And keep in mind that one form of a first order differential equation is this. So this is one of our standard forms. But as we've seen, we can rewrite differential equations in various formats. When we looked at separable differential equations, we said that if we could rewrite the right side into where we had some function of x times some function of y, and we use different letters, I'm not sure, sometimes g, sometimes h, sometimes p, whatever. But if we could rewrite the right side as a product of x functions times y functions, then we could separate this where all the y's on one side, all the x's are on the other side, and then we could integrate. Something else that can be done is, let's suppose that the right side is a quotient, and the numerator could be a function of x or y, or both x and y. And just for sake, I'm going to put a negative with one of those. If we cross multiplied or cleared fractions, we could rewrite this as m of xy dx equals minus n of xy dy. And if we moved all this to the other side, then one way that we could write any first order differential equation is some function of xy times dx plus some function of x and y dy equals 0. So this is one format that we can write differential equations in. Now, while I say that the coefficient of dx is a function of x and y, it could turn out that it's only a function of x or of y or a constant, or it could be of both. Same thing of n. So before we say too much more about that, we want to discuss a little bit about what are known as level curves. Level curves are something that came up in Cal 3 when you start to talk about multivariable calculus, where you're dealing with some function that represents z, and that function is a function of x and y. Now, we're only going to be dealing with functions of x and y here. We're not going to be dealing with 3 variables. But where this comes into play is we're going to be dealing with some partial derivatives. Now, this is still going to be an ordinary differential equation, because in our differential equation that we eventually solve, notice that this differential equation here has no partial of x or partial of y in the actual differential equation. But we might have some kind of connection to the partials eventually, or we might need to use those partials for something. And where partials first come up is when we look at functions of x and y, where we don't have just one input, but we have x inputs and y inputs, and those are related to z. And when we start wanting to make graphs of these 3-dimensional functions, then we begin by looking at contour lines or level curves. And what we do is we let our function or our z value be one constant, and we say for that particular constant, what does that curve look like? So at a particular z value, we might start out when z is 0. What would the x and y curve look like? If we looked in the xy plane, what would we have? Then we might go to another z value, for example, z equals 2, and say when z equals 2, if we look at the x and y plane, what does that curve look like? And once we do enough of that, then we kind of get what kind of looks like a topographic plot to give us an idea, even though this is only in 2 dimensions. If we picture that each of these lines represents different altitudes, different heights coming out of the paper to you, then we can kind of visualize what that looks like 3-dimensionally. So even though we're not dealing with 3 dimensions, sometimes we want to look at specific constants and say when our function is of a certain constant, then how are x and y related? How are x and y related for that particular constant? And then as we change to a different constant, how are x and y related? And we might even want to know, okay, what is the slope of the tangent line on this particular curve? So it's not 3 dimensions. We're letting our function be a specific constant. If you think about when we did isoclines, when we drew direction fields, we would pick a particular value for our constant. X and y themselves were still variables. And we said for that particular constant, what does our XY graph look like? So everywhere on this particular red curve here, when we plug in X, when we plug in Y, we get the same answer for all of those. We have the same constant. So if we want to find the slope of that, keeping in mind that that function is some f, function of x and y equal to a constant, then we need to take the derivative of both sides with respect to x. The derivative of a constant is 0. On the other side, keeping in mind that y is dependent on x, since we have two variables, we need to take partials. We're going to take a derivative with respect to x, and then we're going to take a derivative with respect to y. So if we take the partial of our function with respect to x, and then the partial of our function with respect to y, but since these variables don't match, we pick up a dy dx. Now we could solve that for dy over dx, and I'll just write that real quickly. If we solve that, we would get the opposite of the partial of f with respect to x over the partial of f with respect to y. That will give us the slope of our tangent line on various isoclines, on various level curves. So that's one thing that we could do when we take the derivative, is we could get the slope. But we could also get our total differential. One of the first things we talk about after we talk about partial derivatives are applications of our differentials. Recall that when our function was just a function of one variable, things like y equals f of x, that we were able to estimate the error in y using differentials. And f prime of x times dx gave us the dy. So this is how we calculated the differential dy. We can do the same thing if we have multivariables. The partial of f, or differential f, if our function is two variables, is the partial of f with respect to x times dx plus the partial of f with respect to y dy. Notice if we multiply in this equation each term by dx, we get this. This is the total differential. In one dimension, or when we had one input variable, we were looking at if we make a small change in the x direction, how does that impact a change in the y? Here, if we have x's and y's, if we're making a change in the x and a change in the y, how does that impact how much our function changes? Well, if we're on a level curve, then our function is not changing at all. If f of xy is a constant, then our net change is 0. So how is that related to what we had earlier when we had m as a function of x, y, dx plus n as a function of x, y, dy equals 0? So if we have this, that left side is a total differential of the function f. And if we have the function f, if we are to take the function f and differentiate it, if we take the partial with respect to x and then the partial with respect to y, that's similar to a second derivative. Then we could also take the partial with respect to y first and then the partial with respect to x. And for a given function, those produce the same result. Those produce the same result. So this is how we're going to test if we have an equation in this format, is that a total differential? If it is a total differential, then in that case, m would be the partial of f with respect to x. And n would be the partial of f with respect to y. So if we already have a derivative with respect to x, if we take that and take the derivative of the partial with respect to y, then this would be the derivative of f. If we take n, which is the partial of f with respect to y, and we differentiate it with respect to x, then, let me see, let me not put equal there. This would be equal. So if we take m, which already is a partial of f with respect to x, and then differentiate that with respect to y, then we've differentiated f with x, then y. If we take n, if it's a partial of f with respect to y, and then we differentiate it with respect to x, then this would be f, where we've taken the y partial followed by the x partial. If those two things are equal, then that shows that what we have is indeed the total differential. If they're not equal, then they're not it isn't the total differential. Well, what was the value of knowing if we have the total differential? If indeed we have the total differential, if we know that m equals the partial of f with respect to x, so m is our function that we're looking for. We're looking for what function as a constant has this as its derivative, so we're looking for f. If we know that m is the function we're looking for and differentiate it with respect to x, then we can integrate it with respect to dx. We took the derivative with respect to x. To go backwards, we would integrate it with respect to x. Same thing with n. If n is the partial of f with respect to y, if we want to go back to our function, then to undo it, if we've integrated, or if we've taken the derivative with respect to y, we integrate it with respect to y. So when we do that, then that should give us our function related to x and y. Now you might say, why do I have to do both? Well, when you take the derivative of tongue-tied when I say this. If f is the function of x and y, and you take the derivative of that with respect to x, if you have an x term and a y term, then when you take the partial of this with respect to x, that term goes away. So when we go back to integrate with respect to x, we're not going to get any y terms. We would pick back up our x terms and possibly any constants, but we wouldn't get our y term. Likewise, if we were to take the partial of that with respect to y, our x term would go away. Then when we integrated it with respect to y, we're not going to get any x's back. So when we take our partials, if a term has just an x or just a y, those terms are going to drop. We don't know which terms are missing, so we have to integrate m with respect to x and n with respect to y, and then we have to compare these to see what all terms we need to include in our final solution. So let's look at an example. Let's look at 2xy plus 3 dx plus x squared minus 1 dy equals 0. So first of all, let's determine whether or not this is exact. So if it's exact, then this m has already had the partial done with respect to x, so we need to take the partial with respect to y. So if we take the partial of m with respect to y, everything that's not y we treat as a constant. So 2x is a constant, times the derivative of y is 1. The derivative of 3 is 0, so we get 2x. So when we take the partial of that with respect to y, 2x. Now if this is n, that's already had the partial taken with respect to y, so we want to take the partial of that with respect to x. So the derivative of x squared with respect to x is 2x. The derivative of a constant is 0. So those match. So this is exact. Yes, this is exact. So once we know that it is exact, we solve it. We're going to take m, that's m, and we're going to integrate it with respect to x. Have to be careful because we differentiated it with respect to y so that we could check to see if we had this. If this was a partial derivative of our function with respect to x, then when we take the partial with respect to y, it should match what we get if this is a partial with respect to y, and then we take the partial with respect to x. So we're trying to see if we have that characteristic. If not, then it's not exact, and we have to do something different. But if it is exact, then we work our way backwards. So we take our m, which is a partial with respect to x, so we integrate it with respect to x. So 2 and y coefficients, if we integrate this with respect to x, that's x to the 1 bigger power over that power. Integrate 3 with respect to x, we get 3x, and then we can have a plus c. So that's our function. Now we have to do that with our n. N was x squared minus 1. So since this is exact, x squared minus 1 came from taking a derivative with respect to y, more specifically a partial with respect to y. So we're going to integrate here with respect to y to go backwards. The opposite of taking a derivative with respect to y is to integrate with respect to y. And when we do that, that should give us our big F. So x squared in terms of our variable is a constant, so we integrate that. That's x squared, that's a constant, so we pick up our variable. That's a constant. When we integrate it, we pick up our variable plus c. Notice over here the 2's canceled, so we had, which is x squared y plus 3x plus c is our f of xy. Over here we have x squared minus y plus c, so we have some commonalities. Both of these have an x squared y. We have a 3x that we picked up when we integrated with respect to x. We picked up a y when we integrated with respect to y, and then we can have some arbitrary constants. So our function will be x squared y plus 3x minus y, and we're going to move the constant to the other side. So if we move the constant to the other side, that'll just be c. That's f is the function of f of x and y. Now you might say, I'm not sure why we have the 3x and the y's. Well, let's just check. So if we want to check, let's see if we take our function f. If we take respect to x, is that going to give m? So when we take this function and take the derivative with respect to x, y is a constant. When we take the derivative of x squared, we bring the 2 down, x to the 1 less power. When we take the derivative of 3x, we get 3. And then when we take the derivative of y, since we're taking the derivative with respect to x, or rather the partial, then the derivative of that is just a 0. So that's our m. And if we scroll back up, that's what our m was, 2xy plus 3. So we lost the y term when we did our partial with respect to x. Now if we do our partial of f with respect to y, so if this is f, when we take the derivative of this with respect to y, x squared is a constant, the derivative of y is 1. 3x is a constant, the derivative of a constant is 0. The derivative of y with respect to y is 1, so that's x squared minus 1. And if we scroll back up, that's what n was, x squared minus 1. Our n, we lost the, where did we go? We lost the x term when we took the derivative with respect to y, because that had no y's in it. For m, we lost the y term because we were taking the partial with respect to x that had no x's in it, so that went away. So that's why we have to include both of those. And that's why we have to integrate it both ways, because we can only get the x's back when we integrate with respect to x. We can only get the y's back when we integrate with respect to y. So let's do it. So let's take a look at cosine theta dr minus parentheses r sine theta minus e to the theta d theta equals 0. So if it's going to be exact, it has to fit m dx n dy equals 0. It has to be in this format. And when we take the partial of m with respect to y and the partial of n with respect to x, those have to be equal. M already is a partial of x, or with respect to x, so if we take the other partial, which is with respect to y, n is already a partial with respect to y. If we take the partial with respect to x, then both of these would be f, taking the derivative with respect to x and y, whether we did x first or whether we did y first. So that's how we're going to check to see if it's exact. We need to put it in this format. So if we're going to put it in that format, then we need a plus here. So if we want that to be plus, we can multiply on the inside by a negative and on the outside by a negative. So we can change that to cosine theta dr plus e to the theta minus r sine theta d theta equals 0. If you're not sure if these two things are the same, if we distribute, that's minus r sine theta plus e to the theta plus e to the theta. So this is m, and then this is n. So if it's exact, then if we take all of this, let's see, this has already had the partial done with respect to r, so we need to take the partial of this one with respect to theta. This one has already had a partial with respect to theta, so we need to take the partial here with respect to r. And if it's exact, these will be equal. So the partial of m with respect to theta equals, well, the derivative of cosine theta with respect to theta is minus sine theta. We take this partial, that's the partial of n with respect to r. If r is our variable, then anything that's not r is treated as a constant. So the derivative of this is the derivative of a constant, which is 0. Sine, our variable is r, so this is considered a constant, so we leave it alone. The derivative of r is 1, so we get minus sine theta. So remember, even though r is a variable, and even though theta is a variable, when we're doing partials, if it's not that variable, we treat it as if it's a constant. So that's not an r, so we treat that like it's a constant, so we leave it alone, take the derivative of our variable, r. So those are the same, those match. So this is exact, because those are the same. So if it is exact, then we should be able to work backwards to get our original function. So cosine theta, that came from taking the partial of f with respect to r, e to the theta minus r sine theta. That came from taking the partial of f with respect to theta. So if we want to work backwards, we need to move the partial. We're going to integrate cosine theta with respect to r. Here, to get f, we're going to integrate e to the theta minus r sine theta with respect to theta, just moving the d theta over. So f as a function of x and y, when we integrate cosine, and let's put this as dr instead of partial of r. When we integrate that with respect to r, if r is our variable, we treat cosine as a constant. And if we integrate a constant, we pick up our variable. So there's a constant, pick up our variable, plus c. Then when we integrate here, we get f as a function of x, y. We're integrating here with respect to theta. So when we integrate e to the theta d theta, just like integrating e to the u du is e to the u, this would be e to the theta minus r is the coefficient, so we leave it alone. And when we integrate sine, the integral of sine is minus cosine. So we get e to the theta plus r cosine theta plus c. So we have some common parts, so we don't have to list those twice. This one has a part that's only listed in this one, so we have to include it. So f of xy is e to the theta plus r cosine theta plus a constant, or if we solve it for c, equals a constant. And again, we can check that. If we take the partial of this with respect to r, we should get cosine theta. If we take the partial of it, we should get this. Now, integrating m and integrating n only works if this is exact. If it's not exact, then that's not going to work.